Okay. Okay, so let's start with this. Finding centroids and moment of inertia, are you okay with? They're not going to go away. We're going to do more and more of them as we go on in life. Okay? But do you get the gist of how to actually calculate it? When it comes to an exam, unless I'm really testing that portion, I will give you the moment of inertia. Because that after something else in the problem. Okay? So if that's the case, and I think it's probably safe, let's start with some bending. And we can take, no, not the last one, that was that C one, wasn't it? Let's say, let's use that moment. No. We could. Did we do the 2C channels, or that was one I gave you for homework? We did the 2C channels? Yeah. Let's use that one. We'll set that up with a load. Okay. Let's take that and we'll put a load to it so you can see what happens. And I'll get you the gist of what's going on here, okay? All right. So, I can get my mask to stop fogging up my glasses so I could actually read what I'm writing. All right, so using problem 8.12 for C and I. Determine Okay, so in this diagram, we are going to do this. I don't like that. Okay, so we got that. So there's a bunch of things I'm going to introduce you to here. One is, let's talk about the reactions on this, okay? Oh, I need a number. And we are literally making this up. Patrick, give me a number greater than 10,000 and less than a million.
19,496.
19,496. Want to do pounds or you want to do newtons?
Pounds.
Okay. All right. Frank, give me a distance between pieces here greater than 25 and less than 50.
36.
Okay. Cool. All right. So, remember our friend statics? Yeah, we got it. Yes? But don't remember statics, he's none the dead. Like it or don't like it? We've already had this conversation, right back in the beginning of the semester. It's back. So, first step to this problem is find the reactions. But I want to point out something here. So, based on the diagram of what I drew for the reactions, what are the two possible things I'm looking for? What type of reactions? Which directions can the reactions be? Force. So I got the force pushing down, P. Your reactions have to be what? You got to go vertical for the reaction of that. But because of the reaction type at the one end, what's that lead you to a possibility of having? I could have an x-axis reaction here, couldn't I? Because I'm going to allow it to move. Right? But I only get that if I add what to it? Well, I got a roller out there because that's the triangle with the three rollers. Okay. But I just want you to point out, if this had this instead of that, then we got a reaction in the x direction. Okay. So keep that in mind, because it will come to haunt you, but it won't be for this problem. All right. All right, so very first thing. Free body diagram, correct? Is from that 19,500. We'll go with that.
I want to make it interesting.
Yes. You'll be using your calculator. Doing that in my head. All right. So, what's the reactions? Let's go back and do them the hard way, even though it should be pretty easy to figure this one out. But in order to solve for this, we got to do sum of the forces in the y equal to 0, and sum of the moments equals 0, right? There's no x, but you can do an x, okay? So, can I solve for some of the forces in the y? No. All I can actually do is write this. RL minus P plus RR, okay? So, it helps. Literally, that's the way, when I was a student, that I remember doing it, just because we got used to just doing it. But the reality is, I can't do anything with some of the forces in the x or the y. So, it doesn't help to have sum of forces first. So really the very first equation you should work on is sum of the moments. Okay? And we can solve for those two. Alright? So, first things first. So we got 36 all the way across here, which half of 36 is? 18. At least I was hoping it was 18.
Okay. Oh, by the way, why is this a free body diagram, but that one above is not?
Go ahead, Henry. You're looking at me like you know. I only have the forces shown. Don't have the actual physical reaction to it. They see that? He lives. How are you?
Okay. So, that being said, always, without fail, draw a free body diagram. Okay. So the cool part about this is now if we do the sum of the moments, we are actually looking for P we know. You got to pick one of these to be the pivot point, and I'll give you a choice. You can choose right or you can choose left. Choose one. Let's see. Emma, pick one. Left. Okay. So we're going to do some of the moments about RL. Now, the other bit to this is we want to make sure we choose
A rotation to the moment. You can choose any way you want. Actually, in all fairness, I should have let you choose. Montana, would you choose this one? Yeah, rotation, about RL.
Like, even clockwise.
I pick clockwise. Would you pick clockwise or counterclockwise? Anybody go counterclockwise? There's no right or wrong with this answer, by the way. Just whatever your preference is. So as long as you're consistent and watch your negative signs, everything's gonna work. Okay? If you screw it up, it's because somehow you
mess something up in the algebra. All right, so we're going to do about RL. All right, so that leaves me with P times 18 feet minus RR times 36 feet. Okay? Okay, so is P positive? Yes. So if you like, you can put it in there or you can leave it blank. Just
whatever helps you remember the rotation bit.
Okay? All right, so we're going to solve for P. P comes over to this side of the equation, and it's equal to RR, 36 feet, divided by 18. Okay?
Oh, sorry.
Working that backwards. We know PL, don't we? I'm going to do this. 19,496 pounds times 18 feet minus RR times 36 feet. That way we actually solve for the right thing. RR is that 19,496 pounds, 18 feet, divided by 36 feet. Okay?
Cool. Now I got the right problem. I don't know why I was solving for the force. Because I left it blank. So what do we got for an answer?
$9,748 pounds. Okay? And then ultimately, you should go back and do some of the forces in the y equal to 0 equal to RL minus P plus RR and we're going to get minus RL plus P minus RR, and we're going to get 19,496 pounds minus the 97,484, and that's going to leave us 9,748 pounds. Okay? So we got our reactions now, right? Everybody good?
Remember the statics for that? Yeah. Cool. Well, maybe you don't need it. Oh, yeah, you told me. Said I wouldn't embarrass you with it. But it is pretty damn fun. You know it? Cool. Hello? You know it. You know what the hell's meant means? Should I say? Alright. What happens if there's two forces on the top? Remember all that? Well, we take them all in series and we just keep doing the math, right? Everybody okay? I mean, I picked an easy one for this problem because what I'm going to do next is going to drive you nuts. So I want to start with something simple. Okay? Alright. So cool.
All right. So that's our reactions. Now, let me do this for a minute. And then we're going to come back and do some drawings of this thing. Oh, I guess I need this. I'm going to put an A there, a B there, and a C there, so we got some points of reference here, and you can come out of the way. So this is A, and this would be RL, okay? And this is B minus, okay? So if you think about this, it's B minus, okay? Just before the force. All right.
You don't have to do this in a couple of days to get the hang of this, but I'm going to break it into full, really small segments as we do this, okay? So, if I have a force at B, that's the 19,000 pounds, and I'm trying to figure out what's going to shear. I want to know what's just going to happen just before the force causes the shearing. Okay? So do you remember the shear stuff we did back in the beginning someplace along the way here? God, it wasn't that long ago. Although it feels like 900 years ago, 970 years ago. But that's anyway. So that force at B, we'll want to try and slice that beam in half. Okay? Cool part is we're going to pretend it does. Okay? But I'm really interested in what's happening just before it does it. Okay? So someplace out here, I think I'll do it like this.
We'll put a red. There's just a little bit of material left out here, okay? And that means we have this fictitious force out there, P, okay? And that's really at B.
But just before that point, what's the reaction there? Okay? Is there anything happened to that? We just cut it. or just imagine it beforehand, okay? It should be the reaction of what's RL, okay? So literally what we're gonna do is this. So watch where the fun comes in here, okay? So, nuts. I wanna draw up here. No, I'm gonna do it here. We will start right here. Oops, let's do black. Okay, so this is a shear diagram. Okay, so we start at 0. At point A, here, let's do this. We go up. No, let's make that bolder. We go up. And then we go over until we are here, okay? So everything across that beam until that point of B, okay? So B minus or B prime, no, what did I put it down? I put B prime. B minus is above B prime. B minus, okay, so just before B happens, okay, the force at B. Everything still stays the same. There's no other forces acting on that, okay? So the uplifting force of the reaction is going to lift that whole left side of the beam up until we hit the force T. At B, then it will start going the other way, okay? So, cool. Now, we can actually calculate that. So we want to do V at A is really going to be RL, which is equal to 97,490 pounds. It's the only force acting there, okay? So literally, it's going up to here at 97,480, okay? And I usually put the units down here so you don't have to fight with it, okay? But when I get to VB minus, we're still equal to RL, 9748 pounds, okay? But here comes the kicker. So here's VB, okay? And it's going to go the VB minus, and we got the P now, okay? So VB minus is a positive, and P is a negative because that's the direction it's going. And that reminds me, I didn't do that up here, did I? That's positive. So identifying which direction is positive so you know how to get your signs up. Right? So now I'm right at the point where P's acting on this beam and it's going to slice through it. Okay? Doesn't really, because if it did, we'd never get anything made. But we act like it slices there. I'll show you all why in a minute. But if it's soft enough, it will actually bust through. Okay? Okay. So now with P added to this equation, we're looking for V at B, so it's going to be 9748 pounds minus the 19,496 pounds. And what's that going to be?
Anybody want to guess? Negative 9748. Okay? So that literally means this. We're going over there, and we're going down. And we're going to start that way. Okay? Now, this is what's happening with the diagram now at RL, P, okay, and that's at A, and that's at B. And that's the diagram that goes with that for the free body diagram, okay? And the result of that free body diagram says I got a lot more P than I got R, so I'm going to drive down to what was the neutral axis, right? Zero axis of shear. Make sense? Okay. Now, as we move to the right on our beam, what's going to be the result of all this? It's going to look like this, okay? And then we're going to come back over and we're going back to zero, okay? Actually, wouldn't draw the arrow in there. So let's do the math that goes with this, okay? So V at C is equal to, well, let's do this. What the heck? V plus is equal to VB in this case, okay, which is equal to negative 9748 pounds, okay? And then V of C, so this is point C, that's B, and that's A. Point C is going to be V of B plus the RR. Okay? So V of B was 9,748 pounds negative, plus the reaction at R was 9,748 pounds, and they come out to be 0 pounds. Okay? So far makes sense? Frank? Load? Can you see what he did? All right. I could have done this problem without this diagram. Okay? It's that simple. But the trick is, they're not always going to be simple. You need to draw the diagram. Okay? What I'm looking for is the maximum moment of this problem due to bending. Okay? So I'm going to go for sigma is equal to MC over I. Okay? The I and the C we found from that other problem. But I'm looking for the max moment. Okay? Now, in order to get the max moment will always occur wherever the shear crosses the zero axis. Okay? So it's not going to occur out here because we got nothing really going on. But right there is a good likely spot to have the maximum moment. Okay? Now, bring back my trusty all right. Now life's going to get a wee bit more complicated. So let me zoom in on this. That's our moment. equal to 0. This is in pounds, feet, right? Because we were using feet earlier. Okay. And yeah, hang on to you for a minute. Now, I want to do this. I'm going to draw okay. So, let me zoom in on that so you can see it a little bit. All right. In order to actually do this, this is one of those games they tried to get you to learn in math about doing limits. Remember that stuff? But you remember the phrase, right? Okay. So, if I'm taking a moment about the left-hand edge, okay, and I'm at some really small infinitesimal distance, in this case I pick 0.001 inch, and I got a 36-foot beam, okay, I don't really have any moment like that, okay, but I want you to get used to the concept of what's happening. Okay. From that part out RL, where's my ruler go? I'm holding this end fixed, okay? And I got 0.001 inches here, okay? There'd be a moment because of the reaction for this thing. RL is going to want to twist it up this way, okay? So, very, really small, I don't have a real moment at all, okay? So the moment's going to be 0. As I get out to 18 feet, I should have quite a big moment, okay? So it's always a taper of this thing kind of, as it grows, it's going to become more and more of a moment, right? Because there's a distance to it, okay? Everybody good with that? Kind of a weird concept to explain. Every year I do this. Always looking for a better way. So if you don't get it, let me know, okay? By the way, that reminds me of one of my impromptu chats with the civil students today. If you folks are confused in any class, ask questions. Ask questions to the instructor, come to me, see your advisor, ask your peers, but get some help. No one does this on your own. And if you think you do, let me tell you some other horror stories, okay, but not today. But make sure if you're struggling, that you're not struggling by yourself. Come struggle with some friends, okay? And at least we can help you. The other thing I know is I got to talk to the tutoring director today to find out where all the tutors went and what we're doing about tutors, okay? So anyways, so now we're doing the moments, okay? So literally my moment at L, or at the left side here, and I'll use RL, is going to be equal to 0 because there is no, if I was to do this out, I got RL times 0 feet, okay? There's no distance there, so there's no moment, right? Even though I have 907.48 pounds times 0, anything times 0 feet is 0, correct? Okay, so it's a whole bit with trying to approach where we go, all right? Now, if I take this and I look at the moment about B, I'm going to have a P, all right? But it's not the P I'm after here. It's actually the RB or RL, okay? Because what happened here? RL, but now I picked up a distance of 18 feet, okay? So let me draw this free body diagram. I got that, and I got this. And this is that B minus bit again. I don't have the P out there, okay? What happened just before the P, all right? And then I'm going to show you something really simple here that will make a lot of sense to you and why we do the shear diagram. Everybody okay with just before B, I'm going to have the RL as my force times 18 feet. 17.999999999 just before that slice. Okay. All right. So what is seeing that you picked this number, Patrick? What is 9748 pounds times 18 feet?
175,464.
175,464
Yes.
pound feet. Okay. So this is how this is going to work. Going up here, and I'm going to draw a line like so. And I'm going to label this 17.5464 pound feet. Okay. Now here's one of the coolest things about strength of materials, and you may or may not like it, but I don't really think there's much I can do about it if you don't like it. The area, oops, let's use red. The area of the shear is equal to the value of the moment. Okay? And the proof in that little pudding is okay? It's as simple as that. Now, we have a few minutes left here. The next little step is this. Calculate the other side. This one's easy. We went up and we went down. Okay? So what's it on the other side? If we were to do it, it's the same equation, but with the negative sign. Okay? So in essence, they always wind up back at 0, too. Okay? So the coolest part about this is I have a max moment with M max equal to 17,546 pounds feet. Okay? So literally I can come in here now and we can do sigma is equal to max moment times C over I. So 17,546 1.5464 pounds feet. Anybody remember the C value we had? The Y0. 11.8 inches.
Yeah.
Okay, so we got to multiply that times 12 to get it in feet. And our I for this was no, not multiply it, divide it by 12. How am I thinking here? Divide by 12 inches gives us feet. Okay. What was the I? Inches to the fourth. What is 12 to the fourth? So we got to do 12 inches. 20,000.
736 if you're asking for bulk.
Yep. 20,000.
736.
And that leaves us with feet to the fourth. Okay. Punch that number out really quickly and I'll let you out of here. Okay, do some rounding there and give it to me in 2.23. Okay. Normally we take those into pounds per inch squared, but this works. Okay. Because where we had the units and what we started with. Normally keep track of your units from the beginning and you're better off.
That's second. It's just 2.38.
2.38.
Or I can go to the next.
No, that's fine. 2.38 is close enough for government work. Okay. And that's our stress in this. Quick review, and we'll do this again and again till you get it. Free body diagram, shear diagram, moment diagram. Find your max moment. Get your max moment, then go plug it into the bending stress equation. Pretty cut and dry. Doesn't get any more exciting than that. Just gets more difficult. Okay. We will do these again and again, so don't panic if you didn't get it today.